All right. So the mechanics parts did not record, but all right, good, and the camera is tracking. Excellent. All right, so now it's time to start complex analysis in earnest. So the first thing is, what's the most important concept in, say, real analysis or Calc 1? And we do not have a clock in this room. Oh, no, we do. It's right there. OK, excellent. OK, good. So what's the most important concept in Calc 1 or real analysis? What's the main object we want to study? Derivative. OK. So we need the definition of the derivative. Anybody recall the definition of the derivative? I'll do it at the point x naught. OK. Okay, and I'm doing the point x naught, okay.
Minus f x naught divided by h.
Okay. Has everybody seen another definition? What's the definition you've seen?
F prime of x is equal to the limit as y approaches x of...
So I'll do it as x goes to x naught.
Yeah, okay. Of f of x minus f of x naught over x minus x naught.
So it's not that much work to see that these are equivalent. Let x equal x naught plus h. Okay. What's the definition of the derivative, say, for a function of two variables? Yes?
If there exists a linear transformation.
Okay, good. Okay, so we want a linear transformation.
We can call it J.
Okay.
So that the limit. So yeah.
Let's say R2 to R2. Okay, so we want.
So we want the limit as the magnitude of h goes to 0, where h is.
Okay. So I can just write h goes to the 0 vector.
So the magnitude
Mm-hmm.
of f of x naught plus h.
Good.
Minus f of x naught minus j of h. Or no, j of. Is it h or x?
Well, so you gotta think. So can it?
J of x naught.
You could do j sub x naught or j of x naught times h.
Yeah. Okay.
So it should somehow depend on the point, and then we should have our h vector over here,
And then divided by the magnitude of h.
and then we divide by the magnitude of h. Excellent. So then we would call this j. That would be the derivative. And of course, we don't really need to do it from 2 to 2. We could do it from n to m. And we've got to be careful because the length up here may not be the same as the length up here, because they could have different numbers of components. This is the rigorous definition. The question is going to become, what is the right definition for the derivative of a complex variable? So, we will write z is x plus iy. It's either I is or I am the square root of -1. This is going to be our generic complex number. We will write this as z is in c. We'll write z bar is x minus iy, and that's the complex conjugate. And the question is, which is the right way to define the definition of the derivative? Now let's think about what's going on in real analysis. What kind of paths can you have to approach x naught?
You come from the left, you can come from the right.
Yeah, it's kind of boring. So the real line, those are our two paths. I mean, yes, you could be hopping back and forth, but if you're doing something like that, you might as well just say, well, look, I'll split into coming this way, coming that way. It's boring. Okay? How many of you have seen The Karate Kid? Or the sequel? I think I want the one where he goes to Japan, and they get the secret of Miyagi karate. This is the secret of complex analysis. You want the limit to exist no matter what path you take. On the real line, no matter what path you take is not that restrictive. Oh, I go up, I go down. Wow, 2 things to check. In several variables, to say the limit exists no matter what path you take is extreme. You must be able to handle a path like this. I do not know how much has been done in Math 150, 151. You might have seen examples of functions whose partial derivatives exist along all coordinate axes, but the function is not differentiable. Because if you approach it along other paths, you will get different limits depending on how you approach, even though all the partials exist. So to be differentiable, it is not sufficient for the partials to exist. It's necessary. So what we will find out is that asserting that no matter what path you take, the limit exists and is independent of the path is going to severely restrict which functions are differentiable. So we can either do right now all of trigonometry in a minute, or we can do the 4 differences between real and complex. We'll do both. Does anybody have a preference for the order? Usually first loud voice wins. With no loud voice, first quiet voice wins. Any preference? Trig in a minute or differences between real and complex?
Trig in a minute.
Trig in a minute. Okay. Now, as it's being recorded, we can actually see if it really is a minute later. So just as a quick review, so if this is theta, this is cosine theta, this is sine theta. I will assume we know e to the I theta is cosine theta plus I sine theta. I will assume we know e to the I theta, e to the I phi is e to the I theta plus phi. This is actually a result that needs to be proved. Notationally, it is highly suggestive that this is true. If this is false, this is bad notation. What is 1 over cosine? And what's 1 over sine? Math has bad notation. Okay? So for this notation to be good, we want the exponents to work as you would expect. What this is really is e to the z is a sum and goes from 0 to infinity of z to the n over n factorial. This is a statement that the product of this infinite series with that infinite series is equal to this infinite series. And it's a nice exercise to prove it using the binomial theorem. So if you want a nice job, try to do that. Okay. We ready? All right. 3, 2, 1, go. E to the I theta, e to the minus I theta is e to the 0, which is 1. And you have cosine theta plus I sine theta times cosine theta plus I sine of negative theta, which will be minus I sine theta. When you expand things out, you get cosine squared theta plus sine squared theta is Pythagoras. If I take e to the I theta, e to the I phi, being e to the I theta plus phi, when I expand things out, I'll get cosine theta plus I sine theta, cosine phi plus I sine phi is cosine theta plus phi plus I sine theta plus phi. And if I really want to do it in a minute, I just say now we're done. To expand things out, I'll get cosine theta, cosine phi minus sine theta sine phi. And I'll get plus I times something else. And the only way 2 complex numbers can be equal is the 2 real parts must be the same. So cosine theta plus phi must be this part. So you can basically prove all of trigonometry from this exponential formula. So if you forget your double angle, triple angle identities, your half angle formulas, here's a way to rederive all of them. All right. So hopefully that was close to a minute. All right. So now I want to talk about differences between real and complex. And so I will try to post my lecture notes online as well. My notes are for the most part, fairly rough, but I want to make sure I use the same notation. Do you mind sharing your desk?
No.
Thank you. All right. So I'm going to have my function f be from R to R, and I'm having g be from C to C, and h being from R2 to R2, and they're all differentiable. Now, I have not yet said what it means for a complex function to be differentiable. So just assume one of the definitions we did before generalizes. We'll figure out later which one. So first question. If the function is differentiable once, it is so twice. So what do you think? If my function is differentiable once, it's differentiable twice. No. Okay, can you give me a counterexample?
You take x squared for positive and negative x squared for negative x. So
Okay, good. So one example is f of x equals sine of x times x squared. So this function will be differentiable at the origin, but it will not have two derivatives. Because if you try two derivatives, it's +1 on one direction and -1 on the other. Another one, and I'll get it slightly wrong, is something like maybe x cubed sine of 1 over x. And so as x goes to 0, the sine of 1 over x is going to fluctuate between -1 and 1. The x cubed will kill that, and it will go to 0. Even if I differentiate once, the 1 over x will come out as a 1 over x squared. The x cubed can still beat that. So this function will be differentiable once but not twice. So for real, the answer is a resounding no. What do you think the answer is in complex? Yes. But there's an asterisk. Anybody have any thoughts what the asterisk means? What the asterisk means, let's think. You might be able to figure out there's something more than just being twice differentiable. Infinitely differentiable. So prove to me that it must be infinitely differentiable.
If one is differentiable, it implies twice differentiable, you can take the second one and put it.
Excellent. And then you just, so now let's say f is differentiable. So you now know f prime. So could we then just keep doing this? And again, when you make comments in class, please send me an email after class with the comments you did. This is extremely useful when I need to write letters of recommendation, so I can say, you know, so-and-so got blah, blah, blah. Even if you think it wasn't a big comment in class, I'm not saying this wasn't a big comment, you know, please send me emails. It's also a good way for me to get to know you. It's a good way to just review things in class. So is that a valid proof? We know that if a function is differentiable once, it's differentiable twice. So we start off with f is differentiable. That then implies f prime is differentiable. But we just said whenever a function is differentiable, it's differentiable again. Yes. So in fact, infinitely often. That is very different than real analysis. The existence of one derivative implies the existence of infinitely many. Okay. Question 2. If a function, let's do it this way. If f is infinitely differentiable, then it agrees with its Taylor series in a neighborhood of positive length. So maybe the problem was we were looking at functions that were only differentiable once. And since any complex function which is differentiable once is differentiable infinitely often, it's not fair to look at just real-valued functions that are differentiable just once. So let's look at real-valued functions that are infinitely differentiable. Does its Taylor series agree with the function in a non-trivial interval about the origin? What do you think?
doesn't have to.
Doesn't have to. What about in complex? Yes. Can anybody give me an example, and I know people who have taken probability with me have seen this example, of a function which is infinitely differentiable but does not agree with its Taylor series?
It's e to the -1 over x squared.
if x is not 0, and 0 if x is 0. So this is either one of the 10 best or 10 worst functions in real analysis, depending on your point of view. It is because of functions like this that we have to work damn hard. The way complex analysis gets around this is they say, we're not going to let you be differentiable, so we're not going to study you. So go away, don't bother us. What is wrong with this function? Well, if you want to find its derivative, we can't just use differentiating because we have a discontinuity in definition. Anybody know how you would take the derivative of this? So how would you take the derivative? What would you do?
Just use the definition?
You have to go back to the definition, and you would look at f of x plus h minus f of x over h. Well, when x is 0, you would have e to the negative 1 over h squared, so you'd use L'Hopital's rule. So do people remember L'Hopital's rule? So let's take the limit as x goes to 0 of sine of x over x. So how would you compute this limit?
We take the derivative of the top and try to find the derivative of
And derivative and top is?
so cosine of x, sine of x1, which is 1.
Everybody agree? In some sense, this is wrong. Subtly wrong. We don't have that many steps, so there's not that many places where we could, yes?
The denominator, like, since...
We have 0 over 0.
So, okay.
Derivative of x is 1. We're running out of places. There's only one place left. Yeah. How do you know the derivative of sine of x is cosine of x? What limit do you need to evaluate to get the derivative of sine as cosine? You need to evaluate this limit. So if you use L'Hopital's rule to calculate this limit, that's wrong. This is the most important limit in trigonometry. If there's time at the end of class today, I will talk about how you calculate this and how this is related to the exponential function. The identities from trig, the double angle formula we saw, you can now see, hey, I always wanted, these angle formulas, these angle additions seem very similar to things in complex and adding exponents. That's what's really lurking on. Okay, so the function is this. It has a Taylor series where it turns out all the derivatives at the origin are 0. This function is of extremely rapid decay near the origin. And so if you were to write the Taylor series expansion of this function, you would have f of x is identically 0. And it's only going to agree with the function at the point. Well, given that a Taylor series, at the origin, you would say, f of x is f of 0 plus f prime of 0 x plus ... Well, all of these things are 0 at 0, so by definition, the Taylor series has to agree with the function at the point. It's not that impressive. I chose them to be equal, and they're equal. Great job. You need to be equal at one other point or in a neighborhood for it to be a non-trivial statement. What this means is if I give you a sequence of Taylor coefficients, it does not uniquely determine a function. I can add 1,701 copies of f of x to my function, and the Taylor series does not change at the origin. So a Taylor series does not uniquely determine a function. This is one of the reasons why the central limit theorem is so hard in probability. You need a little bit more. It turns out in complex analysis, a Taylor series will always exist. And so we say a function is analytic if it's given by a Taylor series in some neighborhood. And one of the big theorems in complex analysis is basically a definitional theorem. Differentiability is equivalent to analyticity. But in order to sound impressive when you talk to the students in lower math classes, we don't say differentiable in complex analysis, we say a function is holomorphic. And just, by using that new word, we get to inflate our chests and sound really prestigious. When I was an undergraduate at Yale, they made the sophomore physics classes all numbered in the 400s, so that the physics majors just seemed so much more impressive than all the other majors on campus. Okay. So the next one is, this is a fun one. Question 3. If f is bounded, f need not be constant. So for instance, maybe I want my function to be no more than 1,793 in absolute value. Is it possible to have a function defined on the entire real line that's differentiable and not constant, but bounded?
Yeah.
Okay, can you give me an example? Sine, cosine, 1 over 1 plus x squared. All right, real analysis scores a yes. What about complex? Yeah, complex gets the no this time. I didn't want it to be all yeses for everything, for complex and all. You have to give a positive spin so real feels a little bit good. So real allows you to have a richer set of bounded functions. In complex analysis, if you are differentiable on the entire complex plane and bounded, you must be constant. What this means is you can actually prove a lot of things because we understand the constant functions extremely well. There are not that many mysteries. Now, there are stories about a PhD that was looking at a class of functions and they proved certain properties. And then a few years later, somebody proved that the only functions that satisfied these conditions were the constant functions. And most of these results that were proved were previously known for constant functions. And so the thesis just... Now, you can introduce new techniques which could potentially be used for other things. We will prove the fundamental theorem of algebra by using the fact that a constant function, that a bounded function is constant. So it's a truly, truly wonderful result. And the last one is a little bit more involved. The line integral along any closed curve is 0. So if I have a continuous function and I take a line integral, so I've got to be careful. So this is now we'll be talking about the function h. So if you've taken Math 150, 151 and they've done line integrals, you will have seen that there are plenty of line integrals that are not 0. And so the answer here is no, but the answer in complex is yes. Any differentiable function, it turns out it has a primitive. The line integral turns out to be 0. Another way of saying it is you're in a situation with Stokes' theorem. And you have your function that you can write it as basically the, it's been so long, the curl of something. And so when you integrate it, it's just going to vanish because you'll just have like a potential function. So this is where your Green's theorem is going to be a little bit helpful in terms of some of the perspectives. And so if you are not familiar with Green's theorem, I urge you to just watch that video. Okay, so we've got about 5 minutes left. I had been talking a moment ago about, I think, sines and angle identities. What was the thing I had said I was going to show if there was time? If only I could play back the video in real time.
It was the thing with sin of x over x?
Sin of x over x. Right. Thank you. Okay, so this is the most important integral, limit in trigonometry. So trig. So I can actually write sine of theta as e to the I theta minus e to the minus I theta over 2i. I can write cosine of theta as e to the I theta plus e to the minus I theta over 2. So we had talked before about e to the I theta equals cosine plus I sine. You can actually go backwards and get sines and cosines in terms of this. And this gives you an idea of why they're inheriting things. Let's calculate the derivative of sine. So sine prime at x is the limit as h goes to 0 of sine of x plus h minus the sine of x over h. I'll assume I know the angle addition formula. You can prove that without too much trouble. This is the limit as h goes to 0 of the sine of x cosine of h plus cosine of x sine of h. And for those of you who know hyperbolic trig functions, I'm being very careful in putting parentheses around here. Minus the sine of x divided by h. So we now want to look at this algebra. How should we view this algebra? How should we look at this? We've got 3 terms. Is there an ordering we want to have for those 3 terms? Which terms do you want to combine? Which terms are screaming, bring us together? Yeah, the ones that have the 2 signs. So I'm going to assume you're comfortable with limits. The limit of a sum is the sum of the limits. The limit of a different, so long as the limits exist, you can do this. So this is really the same as the limit as h goes to 0 of sine of x cosine of h minus 1 over h plus the limit as h goes to 0 cosine of x sine of h over h. And now if you look at what's going on over here, how should I write 1? How should I view the 1 here? Any thoughts? What? Yeah, it's cosine of 0. This is really cosine of 0. And so now I have cosine of h minus cosine of 0 plus, I'm sorry, cosine of 0 plus h minus cosine of 0 over. This is the derivative of cosine at 0. And this is the derivative of sine at 0, because I can write this as sine of h minus 0, which is the same as the sine of 0. And now the limit of a product is the product of the limits. This is just sine of x times the derivative of cosine at 0 plus cosine of x derivative of sine at 0. So all the trig derivatives come down to knowing what is the derivative of sine and cosine at 0. This is why we use radians and not degrees, because in radians, this limit is 1. It's not 1 in degrees. So if you think about a physical angle, you'll change the magnitude of h, but not the magnitude of the difference up here. Which do you think is the easier limit? The derivative of cosine at 0 or the derivative of sine at 0? Cosine. Why is the cosine the easier one? Because it's 0. Because I don't have to worry about scale or units. It's just 0. Whereas here, this depends on how I measure my units. If you are willing to assume the Pythagorean theorem, sine squared plus cosine squared equals 1. If you differentiate that, you'll get 2 sine cosine plus 2 cosine sine, or probably with a minus sign with one of them. And now when you put in x equals 0, oh, I'm sorry, we don't know what the derivative of sine is yet. So if you take the derivative of sine squared plus cosine squared, I think we still have like another, we still have like 2 minutes, plenty of time. So let's say we take f of x is sine squared x plus cosine squared x equals 1. Let's assume sine and cosine are differentiable. F prime of x is 2 sine of x sine prime of x plus 2 cosine of x cosine prime of x equals 0. And now if I just take x equals 0, well, we know the sine of 0 is 0. And we know the cosine of 0 is 1, so we get 2 cosine prime of 0 equals 0. So we actually get the derivative of cosine very easily if we allow ourselves to assume that sine and cosine are differentiable functions. The real challenge, the real work is proving that the sine limit is 1. Essentially, all of differential trigonometry comes down to that, and that's the one limit you should do. So if you've never proved that the limit of sine of h over h goes to 1 as h goes to 0, that's a good thing to try to do. All right, this is a good time to stop the class.